Syzygy, episode 58, Astronomical Pancake Theory. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart. Sitting opposite me at the table, as ever, Emily Brunsden. Hey, Emily.
Hello, hello.
We've been away for a couple of weeks. It's been a busy time, busy month.
Has, yeah.
What you been up to?
So we've been at Your Night, which
Yeah.
was really exciting.
We have. So that's the University of York's local researcher demonstration outreach evening down at the Barbican here in York, and they had the massive exhibition space where everyone had their stuff out, and families and kids and everyone out doing stuff. And they also had a bunch of talks, and we did a bit of science-based cabaret, which was kind of fun. It was a huge day.
It was amazing, yeah.
I think everyone from York, all of York came along at one point. It was pretty crowded in there, but lots of fun. So we've been doing that, which means we've been kind of busy. But we're back. We're back now and getting up on the podcast horse again, if that's not too tortured an analogy. We're on a podcast horse, riding along.
Where are we going with this?
I don't know. I'm going to get off the horse now. Off you go. Go away, horse. So today we are talking about something which is sort of relevant to the date, where we're sort of halfway through. As we're recording this, we're halfway through the month of February, and coming up towards the end of February is a very important day for those of us who love food. Of course, it's Shrove Tuesday. And
Pancake
as
Day!
everyone knows, that's Pancake Day, right? Whether you're into the whole Shrove thing and then followed by Lent, or whether you're just like pancakes, it's a really good day to have. Having basically an international day of pancakes is not a bad thing.
I love pancakes.
Me too. Are you a thin pancake person or a thick pancake? Are you like crepey person or big fluffy?
So I have to put some extra caveats into this.
Okay.
For warm pancakes, I like thin, crepey pancakes.
Yeah.
But for cold pikelets with a bit of butter, gets me every time.
I don't know if a pikelet is a thing over here. I've had
to explain pikelets
All right,
before.
so when you say pikelet, what are you talking about?
So they're kind of thick, small pancakes.
Yeah, kind of sort of, you could fit it in your hand easily, couldn't you?
And you eat them cold with a bit of butter, maybe a bit of jam.
Well, they are very good warm.
Marmite.
They are very good warm, but you can eat them.
Well, I used to have them in
cold.
my lunchbox as a kid.
Even just with a bit of butter on them, they're really
yes.
good. But yes, that's a pikelet in Australia, in New Zealand. I don't know if that's a thing over here. Listeners, if pikelets are a thing for you, let us know. You can contact us on the website or on Twitter, send us wherever, all the places you can go, and tell us your pikelet memories. But the reason that we're talking about, I don't know how I think the horse has come back and dragged us off down this tangent. The reason we're talking about pancakes is because it's Pancake Day coming up, and astronomically, pancakes are a thing, apparently. Emily?
Well, they are a thing. Well, I've made them a thing.
Is this the most tenuous link that we've ever made in this podcast? I think it might be.
Well, I can tell you the history of this.
Okay.
So a few years ago, back in 2014, I was we had the Astro Campus open for Science Week, and it happened that the way that the dates fell that particular year, that the night I was working on, the Tuesday night, happened to be Pancake Day.
Right.
And I thought, well, let's celebrate this. How can we mix pancakes and astronomy?
Must be a way. Surely.
Must be a way. And then I looked at a pancake and I thought, you know what? There's a lot of things in astronomy that kind of look like pancakes.
Okay. Name one.
Saturn's rings.
Okay. Yeah. Saturn,
kind of
Saturn is a
flat.
big planet, but the rings go out quite a long way. So I guess a pancake, which is very fat in the middle, maybe it's got like a big blueberry or something in it. And then you got the big fat pancakey bit around the outside. All right. Okay. All right. So you have identified in your usual fashion a bunch of astronomical pancakey things that we can talk about today.
Yeah. Things that look like pancakes in the universe.
And for no other reason than pancakes.
Yeah.
Why not? Okay, so those of you listening at home, you can go and make yourself a batch of pancakes in whichever fashion you like, whether it's the small pikelety ones, the thin, lovely crepey ones, or the big, fat, thick, sort of American-style ones. And then while you're eating your pancakes, you can listen to us nattering about astronomical pancakes. Emily, before we launch ourselves off into the universe and start talking about pancakey things, there is something, it's sort of the primary reason why we get pancakey things in the universe. So we should probably nail that one down first, which is the whole notion of angular momentum, spinniness, you might call it.
Yeah, so there's a concept in physics which is called the conservation of angular momentum.
Yeah.
And this is the reason why we have disks. So first of all, let's break down what this whole conservation of angular momentum means. So the first thing is angular means you've got something to do with rotation, spinny things.
Circles.
Right? Yep. Momentum's an interesting concept. It's a very physicsy concept, but it's something that we also inherently have intuition about as well. So in physics land, if you like, momentum is the product of your mass and your velocity. So if you've got large momentum, then you've got large mass or large velocity or both.
Yeah,
right?
And intuitively that kind of makes sense if you think about, the amount of movingness that a car has. It's got a lot of mass, and if it's moving fast, it's got a lot of inherent momentum attached to it, m times v. Even if it's not moving terribly fast, it's still going to hurt if it hits you. Like, it's the mass and the speed. So that's that. A little bit different for angular stuff, though, isn't it? In that you need to talk about when something's turning around. It's a slightly different way of looking at the mass, and it's a slightly different way of looking at the speed.
Yeah, so there's two ways we can look at angular momentum. We can look at it in terms of a spin, which is something that's spinning on its own axis. So that means that, like the sun, for example, spins on its own axis.
Yeah.
Or we can look at things that have orbital angular momentum.
Right. So it's not necessarily that it's spinning around on its own axis, but it's going circularly around something else.
Yeah. And those two things are kind of actually the same thing, depending on exactly how you put your mass distribution, right?
Yeah.
Orbital angular momentum is the same as spin. It's just that the thing that's orbiting has the mass out in the orbit.
So it can get very quickly very complicated, particularly when you look at the mathematics of it all. But the bottom line is that when you have a certain amount of angular momentum, spinicality, when you have a certain amount of that is conserved. So what do we mean by that?
So conserved means you can't sort of create it spontaneously and you can't destroy it spontaneously. A bit like energy.
Right.
If you look at a system and you look at its change over time, the total, so long as you're not fiddling with the sort of mechanics of the system, you're not fiddling with things like the mass, then the angular momentum is going to be conserved from, per se, position A to position B.
Right. So one of the classic examples of this is your figure skater, right? It's in all of the textbooks, all of the physics textbooks, right? You've got a figure skater doing a spin, and they're spinning around. They've got their arms and legs out, and they're spinning slowly because the mass is sort of further away from their body, from where they're spinning around, from their axis of spin, right? So they've got the mass all spread out. So they're spinning slowly. They draw their arms in, and the mass has moved closer to that central line. So where the mass has changed. That means in order to keep the same amount of spinniness, their angular speeds up. They go faster as they pull their arms in.
Yeah.
And that's an example of conservation of angular momentum, that it's where your mass is and how fast you're turning.
Yeah. So I'm going to give you an equation to help you understand that.
Go on then. We're not frightened.
I love a good equation. So the angular momentum, we use a capital L for this one.
Yep.
I'm not really sure why.
For angular, no.
No, I'm not even going to guess because I'll get in trouble. So if you imagine that whatever this L is, it's a constant. You can't change that number, whatever it is. And that is three things multiplied by together, right? So it starts off with two. It's the radius times the momentum, the linear momentum or the straight line momentum. That's what makes it angular. And remember that momentum is mass times velocity. So if you like, it's radius times mass times velocity.
Okay.
Now, in the case of this figure skater, we weren't changing their mass.
No.
Right?
Their mass is the same. They haven't lost or gained an arm or a leg.
No. So what we have changed, however, is the radius at which that mass is distributed. So in that case, we can say, well, overall, the radius has gone down.
You've drawn your arms and legs in. So your R has gone down, which means
the V must go up.
V has got to go up in order to keep L for angular momentum. L stays the same. And so if R goes down, then V goes up.
Yeah.
Okay. Conservation of angular momentum. There you are.
Yeah,
Done.
exactly. And this sort of collapsing situation is actually really good because we talk about this a lot in astronomy. So what we have in astronomy, though, instead of figure skaters, tend to be things like clouds of gas. And it's these clouds that collapse.
Collapse because of gravity?
Under gravity,
Right.
yeah.
So gravity is drawing everything down together, but if you've got a certain amount of angular momentum, a certain amount of L, then if M is staying the same, because the amount of mass isn't necessarily changing, it's all just a bunch of stuff, then if you're bringing it in closer together, clumping it down, R is going down, which means V is going up.
Yes.
So things speed up as they collapse down.
Yeah.
Okay.
So-
Easy. Done. I don't know what the problem was.
Well, how do you form a disk then out of this?
Ah.
Yeah, it's a little tricky.
Fine. Okay.
Well,
Yep.
it's not that really. It's not too bad. So what you have, if you have a cloud, so let's say you've just got a random cloud of gas. Now you can imagine that every molecule or every atom in your gas cloud has its own peculiar velocity.
Okay.
Right? It's heading off in whatever direction it's whizzing, right? Now, if you took a sum, or if you counted up all the different particles in your gas cloud, there's going to be one direction that's very slightly preferred, even in a random cloud.
Okay, so what you're saying is we're setting ourselves up with a random cloud where things are moving in all sorts of directions, but one is going to be just ever so slightly randomly, we're kind of just ever so slightly going this way.
Yeah.
Okay.
Because nothing is stationary in the universe, right?
No.
So there's going to be some sort of very slight preferential rotation axis.
Sure.
And then as that cloud starts to collapse, that particular axis is amplified. Because what happens is, as you have your gas molecules, for example, colliding with one another, let's say you've started spinning in a clockwise direction,
Sure.
right? So anything that's kind of perpendicular to that, that's pointing upwards or downwards, then they tend to cancel out over time as the cloud collapses. So all your upward moving particles cancel out with your downward moving particles, and they start to get dragged along with the overall spin of the cloud.
So that tiny imbalance grows and grows and grows because everything else cancels out, and that just one little, we were going clockwise, now becomes, guess what, everyone? We're all going clockwise in a big way.
Yeah, and so your sort of ups and downs start to cancel, which means you squish everything into a single plane, which makes a disk.
Okay, that makes sense. Right, so that gives us a little bit of a grip in sort of angular momentum 101 as applied to astrophysics, turning clouds of stuff into a disk. Now we can talk pancakes. We're going to start with Jupiter? Not Jupiter, although Jupiter does have rings, doesn't it? We're going to start with Saturn?
So I'll talk about all the astronomical fun things that we have, and then we can talk about maybe why
Okay, sounds
these
good.
things actually turn into pancakes.
Because, I mean, it's got to be a reason. It's not just coincidence.
No, it's not. It's all physics in the end, isn't it? It's all physics. So the first thing is when I did this research for this show, I thought, well, how are we going to make this kind of interesting? How are we going to keep the context of what these astronomical things are in the context of pancakes?
Okay.
So I thought, well, maybe we can do some sums. I like a few sums.
Because that's always good for an audio medium is let's do some mental mathematics. Yeah, good.
Well, to be fair, I used a calculator for these.
All right.
So I did some sums, and I thought, well, if I scaled the different pancake-like objects that we have in the universe to being the size of a dinner plate.
Mm-hmm. Like a nice big pancake.
Yeah. How thick would all of these be?
Okay. So would they be a crepey type pancake? Would they be a big fluffy one? Or would they be just a stupidly thick one? Or would they be sort of, an atom thin?
Yeah. And I think that's quite useful because it kind of gives you some scales about discs and
Sure.
pancakes and other astronomical objects.
Okay. All right.
So if we start with Saturn.
Let's do that.
So Saturn is definitely your typical pikelet.
Right. In what sense? That it's squat and thick.
Yeah, so
Okay.
if Saturn's rings were scaled to be the size of a dinner plate, then they would end up being about 4 centimeters thick.
That's quite thick. That's
Yeah.
even cooking that, I think, would be a challenge. 4 centimeters and it's a dinner plate. That is quite thick.
That's a hearty meal.
So, I always thought, okay, I'm quite surprised by that because I thought that Saturn's rings were really quite thin. So I'm wrong about that.
Yeah, so it's all about scale. So
Okay.
Saturn's rings are sort of a bit squat, I guess, in terms of the scales of what we're going to also be talking about with these other disks. So the actual, if you like, radial area that the rings are spread out over, or the diameter that they're spread out over, is fairly small compared to the thickness of the rings themselves.
Okay. Do you have a sense of, I'm imagining my dinner plate, that's the diameter of the rings. How big is Saturn sitting in the middle of that dinner plate?
That's a good question. I didn't do the sums on that one.
We'll have to have a look at that one.
Yeah, it's definitely bigger than a blueberry, though.
Right. Okay. So it's not a tiny little thing in the middle. It would be a, maybe some modest sized piece of fruit sitting in the middle of the plate there.
Yeah.
Okay.
But there's lots of interesting physics that goes on in the rings of Saturn. So what are the rings? They're not.
Yeah, there's a good place to start.
They're not actually pancake material,
They're
really.
not. So what are they? What are they made of?
So they're tiny little bits of ice and rock that are orbiting around Saturn. And they orbit in particular structures. So they look like rings because instead of being sort of a solid disk that goes from Saturn outwards, then you've got gaps in the rings. Some of them have very, very famous names like the Cassini division, the Encke gap and things like this, which separates them into distinct ring-like structures rather than being smooth.
Yeah, I mean, you see some of the really high-resolution images that we've got of Saturn, which are stunning, by the way. And I know that you tend to sort of feel a bit like, oh, Saturn, here we go again. It's not your favorite of the planets. We have established that. But it's still pretty awesome. And the rings are absolutely stunning in high resolution. But they're also incredibly complex.
Really complex. And there's a lot of amazing physics that goes on in those rings as well.
Okay, so what is going on? Why the complexity?
So what's happening is that you've got lots of different interactions between the rings and Saturn itself and Saturn's moons. So Saturn has lots of different moons, but the most...
It does, doesn't it? It's got like a couple of dozen?
Yeah, more than 60, I think.
Wow.
Because it's got the most moons in the solar system now.
Oh, that's right. Yeah.
Yeah, it's overtaken Jupiter. So, but most of those moons are very, very far away or very, very small. Some of the significant ones are things like Titan. And Titan is very, very large. It's one of the largest moons in our solar system. And these moons create what we call orbital resonances in the rings of Saturn. So what happens is instead of having this beautiful smooth distribution of the ice and rock and lumps in the rings, you get bits where it's gravitationally unstable for stuff to be there.
Right. So because you've got a very, very large planet around which the rings go and around which the moons go, but then you've also got some pretty sizable lumps of moon out there going around periodically, that interaction means that there's some fairly complicated gravitational mathematics going on in there. We won't delve into that too far, but what you're saying is that at certain distances, at certain periods, or in certain places throughout the rings, you just can't get stable orbiting or stable bits of ring there. Just can't happen.
So this happens when you might have, for example, half of the orbital period of Titan, or 1/3, or things that become integers as you scale them up. So these are what resonances are.
That's the thing about orbits, isn't it? Is that the orbital period is related to how far away you are from the thing in the middle. The orbit around the sun of all the planets is entirely dependent on how far away from the sun the planet is. Similarly, going around Saturn, it's how far away you are from Saturn. And so you'll get these at a particular radius, a particular distance from the planet, and presumably from the moon, you'll get these places where it just doesn't work here. If you put something in there, it's going to go somewhere else. It's unstable. So that gives us the gaps.
Some of the gaps are caused by these resonances. Some of them are also caused by what we call shepherd moons, which are inside the rings itself. So these are smaller moons. And again, most of those are also resonances. I think there's sometimes a bit of a misconception with shepherd moons that they orbit in a gap that they've kind of cleared, but then that's not necessarily the reason why all the gaps are there. They're not all got shepherd moons in them.
Right.
They're also, again, resonances of the orbits of the shepherd moons.
Right. Okay, so a couple of questions. First of all, are the shepherd moons actual moons? Are they counted among the 60-plus moons?
They are. They're real moons.
Okay.
So they're reasonably sized. They're not as big as Titan and got atmospheres and things like that.
But they're bigger chunks of stuff.
They're bigger spherical chunks of stuff.
Ploughing their way through the ring system. I mean, there's some of the high-res photos showing these shepherd moons quite literally ploughing their way through, and you can see the wake behind them and in front of them of the materials. Beautiful stuff. We'll as usual, put the links in the show notes. Okay, so sometimes the gaps are caused by lumps of stuff and sometimes they're not. They're just these resonances, or they're also these resonances.
Yeah, so that congregates or correlate, what am I trying to say? Corrals, there we go.
Yes.
Corrals all the material into these defined ring kind of structures. And all the kind of the physics that's going on here is all related to what we'll come back to when we talk about actually why you have disks in the first place, which is all angular momentum.
Yeah. It's all about spinny stuff. And there's a lot of spinny stuff in the universe, as we find. It's everywhere. everywhere. So if you're paying attention at school out there in listener land, pay attention to the spinny stuff. Anytime something's turning around, it's important.
It's hard, but it's important.
Yeah. I remember doing in physics at school and then at university and going, oh, my brain hurts. But you have to pay attention because it's everywhere. All right.
Right. So moving on, we can talk about some other disky things.
Sounds good.
So you might have noticed, for example, that all the planets in the solar system orbit in what is basically a disk or a plane.
That is true. I mean, not a perfect plane. Some of the planets are sort of up a bit and down a bit, but not very much.
No. In fact, the one that the rogue at the moment is Mercury.
Mm-hmm.
I say at the moment because it used to be that Pluto was the real rogue, right?
Yes, but as we have talked about on many occasions and still is controversial out there in the world of astronomy, Pluto's not a planet. Doesn't count.
No.
But it's up at quite an angle, isn't it?
It is. So Pluto's up at 17 degrees.
Which is a lot.
At maximum, yeah. So that's quite a lot.
Yeah.
So now the title holder for the most eccentric, if you like, moving out of the plane planet is now Mercury. And Mercury moves out about 6 degrees.
Okay.
6 or 7.
So that's not zero, but it's not enormous either. Okay, so going back to what you started before, which is we've got a dinner plate.
Yeah.
And now the dinner plate is the size of the solar system. What, just going out to Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Going out to Neptune?
Yep.
So
well,
Neptune's...
actually, I did the solar system. So, yeah, I went around a bit in circles with these sums on the solar system because there's lots of different ways you could maybe calculate the size of, or let's say you wanted to calculate the width, if you like, of this plane of the solar system. And there's lots of ways you could do it. And I did try and look for kind of a definite answer as to how wide is the ecliptic plane, but not on the sky because that's a different astrological meaning. So how wide, if you like, is this plane of all the planets' orbits?
Yeah.
And it's a hard number to find, actually. And I'm sorry if people have spent a lot of time measuring this and trying to figure it out. I suspect, actually, it's not really a number that astronomers usually care about
I don't imagine it would come up terribly often.
So what I sort of did was I thought, well, if we took the planet Mercury and we want to make sure that Mercury fits even on its tilt, we might make sure that Mercury fits into this pancake. Then how thick would the pancake have to be? Because you've got to sort of scale it as to Mercury's orbit. So it turns out if you do that, the pancake comes out incredibly thin.
Right, okay.
So it's only 0.1 of a millimetre thin.
Oh, that is a very thin crepe. That's about as thin as a crepe could be, 0.1 of a millimetre. Yeah.
You might have to roll that one up to eat it.
I think so. Little squeeze of lemon and some sugar, but you'll be rolling that one.
So it's a really crepey. Interestingly, if you did include Pluto as a planet and you wanted to include Pluto in your pancake.
So let's do that.
Then you'd have to have a pancake that's 3 centimetres thick.
That makes a huge difference. So Pluto, were it a planet, is tilted much, much more. And of course, it's much further out than Mercury by an extraordinarily long way.
Yeah.
And so that means a much, much thicker pancake.
So do you understand why now Pluto is not a planet? It just doesn't fit into the pancake.
Sorry, Pluto. You make the batter just a bit too thick. We can't cook this. It's not going to work. Okay.
So interesting enough about the solar system. We talk about angular momentum and mass in the solar system. Now, you're probably aware that we've got a star in the centre of our solar system.
It is one of the defining things of the solar system. It's even in the name.
Yep.
Yeah.
Indeed. Now, the sun's a pretty big object in the solar system. In fact, it contains something like 99.8% of all the mass in the solar system.
Yeah.
So it's
fairly important.
Dominant in terms of the mass.
Yeah.
So, however, when it comes to the angular momentum distribution, so that means if you sum up all the different parts of the solar system, how much angular momentum they have, it turns out that the sun only has something like 3%.
That's amazing. And is that because, going back to our angular momentum is radius and mass and velocity, right? The sun has got all the mass, but if we're talking about spinning around the center of the sun, then its radius in comparison to the size of the whole solar system is really small. And so its contribution, even though it's got all the mass, its contribution to the angular momentum is really small.
Yeah.
Whereas Jupiter, which has got relatively small mass compared to the sun, but is a really long way away, so its R times M times V is actually really big.
Yeah. In fact, Jupiter has about 60% of the angular momentum
Serious?
of the solar system.
Oh my God, that's nuts.
It's crazy, yeah.
Wow.
And so these big gas giants that are orbiting quite far from the sun actually hold most of the angular momentum budget.
Wow.
Which is really interesting because if you took a very classical approach to collapsing gas clouds, you find that, first of all, the solar system is not whizzing around as quickly as it really should be. So if you really did take this calculation of L is m times v times the radius, then you end up with something by the time you've collapsed down the cloud that was going to form the entire solar system down to what we have today, the sun should be spinning at several times per second or something
Really?
crazy. Yeah.
Okay, and it's not.
It's clearly not.
We can see that.
No, it's going around about once a month. But yeah, so there's been a huge shed of angular momentum in the solar system. And so despite we having this really true physical law that you can't, the angular momentum must be conserved, we actually have to get rid of a lot of it if we're going to explain the evolution of our own solar system.
And I mean, when we say that angular momentum has to be conserved, in physics, you talk about systems and closed systems, and I guess the solar system perhaps isn't completely closed, that it is possible for angular momentum to be lost. How?
Yeah, well, this is really interesting. And so this is where we've had to start to think about actually what other physics impacts the formation of planets and stars. Because we have to get down from something like what we initially had in this cloud down to 1/10,000,000th of the angular momentum. So we had to shed 9 out of 10 millionths. Is that a good way to write that?
A lot.
We
had to shed almost all of it.
Almost all of it, yeah.
Okay. Do we know?
Over the course of formation.
How?
Yeah, so there's lots of ways you can do this.
Yep.
Now, one of the most easy to, I guess, get your head around and easiest way to dump a whole lot of angular momentum very, very quickly
Should you need to, in a hurry.
is instead of forming one star, to form 2
Right.
or 3.
Yeah.
So like something like a binary star system.
I'm just putting my hand up at this point, Emily. You have noticed that we do only have one.
Yeah.
I see a problem with this theory. We definitely only have one star in our solar system.
There are some people, and I'm not going to say they're astronomers because I don't think they are. But I did find a website where some people do believe that the sun is a binary, and I'm very confused by that, and I'm just not really going to go any further down that particular line of reasoning.
Always behind the sun? Is that the idea?
I don't know.
Okay, well let's put that one aside for the time being.
It is a useful concept for other systems,
sure.
Right? Lots of other binary systems exist, and many of them have planets as well. So that helps the maths, at least for those particular systems.
Okay, that's one way to do it. Maybe not in our case.
No. Now, the thing to remember is that when stars are formed, they are pretty nasty little objects.
Yeah,
right?
I remember you saying they're really violent.
Yeah, they're not like cute, cuddly little infant stars. They are terrors, utter terrors. So they have this protostar that's kind of just been formed. It's got this big disk. Now, at this point, we imagine this disk to be kind of a bit more like the rings of Saturn in terms of being kind of clumpy bits of stuff, but more smoothed out than what we see in the solar system today, which is just a few lumps.
Yeah.
Now, there's a lot of disk mechanics that you've got to kind of start to put into your models if you want to understand how solar systems form. You've got to have, for example, friction. So you've got to have bits of rock rubbing up against each other and heating each other. And one of the key things is you've got to pass a lot of the angular momentum that the star has out into the disk. It's kind of like you've got to give the angular momentum that the initial star would have had to where Jupiter is today.
Okay.
Right? It's got to move,
sure.
if that makes sense.
Sure.
And so the ways you can do this are, first of all, you've got some winds that are going to be really, really important. And this is important because you're changing mass, right? So this is why angular momentum is conserved as a kind of only approximate, because you're moving the mass distribution around. So you're moving the mass off the surface of the star, you're pushing it out into the disk, it changes things in the disk, it ionizes material.
So you're talking about solar wind here, stuff which is coming off or from the star and moving outwards because the sun is a, big, horrible, violent ball of death. And it's sending stuff out into the solar system. And that's it's stuff that's distributing mass.
Yes.
And so that's changing where the angular momentum is situated, in a sense. If you think about it being situated with the mass, that makes sense, then it's moving outwards.
And some of it is lost. I mean, there are energy losses in these processes, right? So when friction's a great energy loss, for example, the wind's pushing into things, ionizing, all of these are energy loss mechanisms. But jets coming out of these pre-stars or protostars. But one of the biggest things that we're trying to understand is actually the contribution of the magnetic field.
Okay.
Because magnetic fields are really, really important when stars are just born. They're nasty, they're violent, but there's probably lots of interactions with these magnetic fields in the early disks that are forming around these stars. And so if you've got magnetism, which is another force kind of entering the equation as well, then you're messing up again.
Yeah.
How things are structured.
Just the maths alone is horrible. You try to figure out what the hell's going on physically. Okay.
So this is an area of active research, which is really interesting because it sort of comes from a very basic kind of, if we just take this conservation law, how fast should the planets be orbiting? How fast should the sun be spinning today?
Yeah, easy.
Oh,
easy,
hang on. We've got to actually explain all this stuff in the middle.
Not so easy.
Yeah.
Cool. Okay.
So that's quite fun. Now, of course, we can also use other planetary systems in the universe to help us with
Sure.
this as
Okay.
well.
So we've started with Saturn. We've gone to our solar system. Let's look elsewhere. Move out.
Yeah, so we have a pretty good sample of nearby stars that have planetary disks around them, kind of like the sun would have in its early days. Now, here's our pancakes coming back in. More than 85% of these disks are less than 5 millimeters thick as a pancake.
Okay, so now just backing up a second, you said that the solar system, if we ignore Pluto, is a fraction of a millimeter. If we include Pluto, then it was how thick?
3 centimeters.
3 centimeters. Now, you're saying if we go and look at, how representative is that? If we go and look at other nearby solar systems, planetary systems around other stars, then 85% of them are 5 millimeters
or less.
Or less.
Yeah.
So that's a fairly thin, sort of crepey style thing is the norm.
Yeah. I mean, I have to be honest here that I didn't do that calculation using the planets in those systems. It's based on the width of the disk itself.
Okay.
So probably the width of our disk would have been similar, and Mercury's just going a little bit crazy later on.
Mercury! We've talked to you about this.
Yeah, so we have lots of these examples, and there's some beautiful, beautiful pictures, including from the Hubble Space Telescope, of these planet-forming stars, often in the constellation of Orion. That's our sort of next-door giant stellar nursery. So we can see lots of new stars being formed
Good
there.
place to look.
Yeah, lots of disks. Really, really pretty. So we got lots of information coming from those kind of areas. So it's really nice that we have these other systems that we can look
and
to as well.
it's really nice that we're able to finally, I mean, after a very long time of guessing, we're now actually able to see whether or not our local environment, our neighborhood is the norm, or are we a bit different? And turns out, no, it looks pretty familiar.
Yeah, we mostly are pretty normal.
Yeah, which is, I guess, comforting or boring, depending on your point of view.
Yeah. Okay, so let's take another step back out.
Yep.
Let's have a look at the next scale of disks.
All right, so we've gone our solar system, other solar systems within the galaxy. So, galaxy? Sized?
Yeah, you might have noticed that a lot of galaxies are kind of disc-shaped as well.
Well, and you can even see that in our galaxy, even though we can't see the Milky Way from outside it because we're inside it, and that's how that works. The fact that you can see that band of the Milky Way, that is the disk. That's the galaxy.
Yeah.
We're kind of looking through it there. So if you go out on a really clear night, do that. We can't say that enough. Really clear night, go and see the band of the Milky Way. That is the galaxy.
And we can see lots of other galaxies just like our own. I mean, the Whirlpool Galaxy, the Andromeda Galaxy, these are the famous images of beautiful, what we call grand spiral galaxies.
I mean, they're not all like that. Some of them are sort of blobby and some of them are stretched out. But the spiral ones
the
are
pancakey ones.
Stunning.
Yeah.
Stunning things.
We're not going to talk about the blobby ones because I don't think they'd make... They're more for the donut episode, I think.
Donuts or dough balls.
Yeah.
That's sort of, we'll leave that for another time.
Yeah. But we'll talk about...
International Dough Ball Day.
We'll talk about the pancakey ones. Now, you could have a go at making your own spiral galaxy pancake, I reckon.
Yeah, I think that'd be good.
I think if you had some chocolate batter and you had some vanilla batter, so you
Nice.
could make a nice swirly spiral pancake.
I'm getting hungry now.
Now, for your scale model for your galaxy to
If
be
we
complete,
had a galaxy the size of a dinner plate,
it would be 2 millimeters thick.
I'm a little bit surprised by that. I would have looking out at the night sky, looking at that Milky Way stretching across, looking at pictures of, because I mean, some lovely pictures of spiral galaxies side on. Some of them we're looking at them like direct face on, and they're amazing structures, and some of them are absolutely side on, and they kind of look thick to me. So I would have thought that it would be thicker than that.
Yeah, I mean, I have to also say and admit that I didn't include the central bulge.
Okay, so you're talking about the disk.
So I'm really talking
bit.
about the disc. Yep. Yeah, how big's the disc? And we've talked about before, we have a thin disc and a thick disc. And so I took the thick disc and basically scaled from there.
Okay.
So we have these beautiful spiral galaxies as pancakes. And so the reason why they're disc shaped is exactly the same reason as why we have planetary discs that go on to form solar systems. Is because the galaxy kind of, the angular momentum is holding it into this disk shape. You had an overall preference for some kind of rotation axis, and that pulls everything else into a disk.
Kind of staggering, isn't it? That I can almost get a grip on a planetary system forming out of a big ball of gas that just happens to have a preference for one direction. And even though the solar system is very big, I can just sort of get a bit of a grip on that. But when you start talking about things the size of galaxies, my head starts to implode a little bit just at the concept of an enormous primordial ball of galactic dust or intergalactic dust that then collapses down and forms a huge galaxy because there was a tiny, tiny little preference for we're going to go this way, not that way.
Well, actually, we don't think that happened.
Okay, that would be why my intuition's failing then.
No, but that's a very reasonable thing to assume. You
Sure.
assume that, okay, we form stars from a collapsing cloud of gas and dust, so surely galaxies are just that on a larger scale.
All right then, blow my mind. How does it work?
We actually have more evidence to suggest that galaxies are formed from a bottom-up model than a top-down model.
As in galaxies form out of the constituent parts, not the other way around. It's what, stars and solar systems first clumping together to make galaxies?
Probably,
Really?
yeah. And probably even if you go back to the really early days, probably we're talking about things like globular clusters forming first and they seeding galaxies.
Wow.
And seeding the kind of congregation of material. We've also got dark matter, which plays a hugely important role in pulling together matter into
Which we still don't even understand, but let's
But it's there and it has to happen,
You can
otherwise
see
we
the
won't have
effects.
galaxies at all.
Right. So let's just factor that into the calculations.
Yeah, so our best the models are saying that actually we start with mostly smaller stuff and you kind of build up from there, which means it's bottom up rather than top down as, have a large thing that collapses down.
So where does the preferential spinniness come from in that sense then?
Well, you've still got lots of objects that are gravitationally bound to one another.
Okay.
They're all still, gravity's a thing that's interacting with all of these different things. And so there's still gravitational forces and there's still some preference of those forces in a particular direction or some preference of the movement in a particular direction.
So it's the same idea. It's just not forming a galaxy out of a huge ball of gas. It's forming a galaxy out of a huge cluster of
star clusters, clumps of
that
gas,
kind of thing. And so it's the same.
stars,
It's the same principle. You're just dealing with slightly larger constituent parts.
Yeah.
Okay. So the same principle of even though everything's moving in roughly random directions, this tiny preference gets amplified and amplified and amplified as it all collapses together to form this galactic structure. Cool.
And then we have another interesting piece of physics which we add in there, which makes the disk of the galaxy not just a smooth object, right?
Yeah.
We've got these beautiful structures we call spiral arms that go through.
So what's that about?
So these are called density waves.
Mm-hmm.
So these are actually traveling waves of material, which means that it works in kind of the same way as sound works in air. So the way that sound travels in air is you get a compression of the air and then when the wave comes up and then you get a rarefication or becomes less dense, the air, as it sort of passes through.
Right. The noise moving through the air is these molecules scrunching together and then moving apart, and then the next molecule over gets scrunched and with the one in front of it, and that scrunchiness sort of moves its way across as a pressure wave. That's what sound is.
So if I speak to you on the other side of the room, the actual molecules that come out of my mouth aren't the same ones that go into your ear.
No, your breath isn't the thing that I hear. It's your breath pushing against the air in front of it, which pushes against the air in front of it, which pushes against the air in front of it. And eventually all that push gets to me. Is that the similar sort of thing that's happening in a galaxy?
So sound waves are these waves traveling through air.
Yeah.
Density waves traveling through galaxies just travel through gas and dust and stars.
Cool. Except using gravity, presumably, instead of instead of what, electromagnetism, which is what it is for molecules.
Yeah, so
Yeah.
so you get bits where everything gets compressed. So these are the arms. And then you get bits where everything gets sort of pushed away again, rarefied.
Cool. And they're traveling waves? Does that
Yeah.
mean the as you're going around the galaxy, those arms are moving?
Yeah, so they're very slowly moving over time as well. So individual stars may sometimes be in spiral arms, or it will move out of them very, very slowly.
So the wave will pass by.
Yeah.
Wow, that's amazing. That's really cool. Like, I knew that the galaxies were rotating. I just assumed that all the stars were rotating in sync with that is what's rotating. But you're saying that's a little bit different. It's a
bit
wave
different.
moving through the stars. That's very cool.
Because if you take the stars that are moving at the very center of the galaxy, just like the planets in our solar system, they're orbiting the galaxy very quickly. Whereas stars out, say, where the sun are orbiting a bit slower. So the stars that are close to the center of the galaxy do lap us all the time, right? Interior stars. So the whole galaxy doesn't rotate like a dinner plate, like a disc.
It's not rotating as one.
It's kind of got this differential rotation that means that you got faster things closer to the
And then
center.
superimposed on top of that are these enormous wave structures, which is the arms.
Yeah, very, very slow moving, we must
That's
say. They're
cool.
not. But yeah, they're interestingly compressing everything into these
That's
spiral
cool.
arms.
Are we currently in an arm or not?
We're in what we call a spur.
No, that doesn't sound nearly as interesting.
I think that's really a way to make us feel better about the fact we're not
We're
quite
not
in an arm.
but we are in a spur. Yeah, thanks.
So it's a little bit
Whatever.
of a kind of like tiny finger off the side of an arm.
We're in it too.
So we're in the Orion
We're
spur
special.
off the Sagittarius arm.
Cool. Okay. All right. So, getting back to our pancake analogy, how thick was the galaxy? Was
2 millimeters. About a 10p coin.
Yeah. All right. So that's probably a bit of a stodgy crepe. That's not your really thin French crepe, but it's not
I reckon
full-on
that's probably
thick.
about right if you want to
Yeah.
have a bit of butter.
Yeah.
I think our fraction of a millimeter that we had with the solar system.
Okay.
I'm a bit worried that
Oh, yeah, I
I
mean,
might
that's-
lose my butter out of the
Yeah,
pancake.
that's barely even there. Yeah. Okay, so
Might
the
not be
galaxy is a
satisfying.
reasonable pancake. Okay, all right.
That's kind of I'm leaning towards the galaxy. It's one of my favorites.
All right.
And yeah, I've got a final one
Yeah.
about discs. And
Go
this
on
is
then.
something we've mentioned on the podcast several times with these discs. Go on, you know it's going to be one of your favorite topics.
Okay, well, look, I mean, we've been moving our way out and up in size, but I can't think of a larger disc-like structure than a galaxy. I mean, you get galactic clusters and things like that, but they're not sort of discs, really. I don't think, and the large-scale structure of the universe is not really disc-like. So I think we're going in a different direction. I'm going to hazard a guess here and say, are we talking about the accretion discs around black holes?
Everyone loves a good accretion disc
Yep,
around a black
okay.
hole.
Points for me, 5 points for Chris. Accretion disk, black holes. Go on then. What are we talking about?
Yeah, so black holes we've talked about several times. They're these kind of enigmas of astronomy, if you like.
They are, yes.
So black holes themselves are kind of a weird theoretical but observable yet singularity event where you've got a whole lot of mass and a very, very tiny volume, which means that light can't escape from these black holes.
Yeah,
Hence-
it's where the laws of physics break down, basically.
Yeah.
If you've got so much mass in such a small space that even Einstein's general theory of relativity goes, I don't know, I guess you've got a singularity. It's all collapsed down to nothing. Let's call that a black hole. And we can't see them, except that we kind of can.
Well, we can see these accretion disks.
Yeah.
And that's the exciting thing. So the black hole themselves, light can't escape, so there's no way that we can see them. But they do have these disks around them of rotating material that's in many cases falling into the black hole as well, which means that it's rotating and it's got lots of heat coming into that disk, which means we can take images of it because that is putting off some light.
Yep.
And that's indeed what we saw when we saw this beautiful black hole image as well.
Yes.
We saw some of the
Yeah.
material
When was that? Was that
swirling
like a
around
year
the black
ago?
hole.
When was that
Yeah,
now?
it would have been about a year ago.
So that was
Yeah.
cool. So actual image of a supermassive black hole.
Yeah,
That
and you should
was
definitely
fun.
check out the episode because it's not quite as straightforward as
It's not.
red ring as the disc, but
Yeah.
it's actually really, really interesting.
Yeah. So again, what we're seeing there is not the black hole itself, because that's problematic. We're seeing its impact on the stuff swirling around it. So tell us about this accretion disk then.
Yeah, so we think this happens for most types of black holes. If there's any material in the area, just like if planets are orbiting a very large mass like the sun, you can have smaller bits of material orbiting your black hole, which has
Sure.
got a large mass. And this can actually be in a very, very stable orbital situation. So you can have quite a lot of material going around for quite a long time.
Yeah, I mean, people think of black holes as kind of like an enormous sort of some combination of a bathtub plug hole sucking everything down it, or a Hoover or something like that, vacuum cleaner. But it's not. I mean, it's really, really dense, but it's just gravity. You know, it's no different from any other really massive thing with a lot of gravitational force that can have things orbiting around it. If you get too close, then things get really problematic and it can tear you apart. But otherwise, you can be in orbit around a black hole in the same way that you can be in orbit around the sun or the Earth. That's not a problem.
Yeah. So some black holes are just merrily sitting there with their own accretion disks, not doing terribly much. But some of them are doing really exciting stuff.
And that's where it's fun.
And that's where it's fun. Because when you have accretion, then you've got energy being released. And that's when these black holes really show their nasty side, if you like. So we've talked about black holes, for example, in the centers of galaxies, active galaxies, where the infalling material gets shot out in jets and you get
really energetic jets.
Crazy amounts of energy being released. You've got big accretion disks that are getting very, very hot, and then they're enshrouded in sort of larger structures, and they're holding together, of course, the entire galaxy around them. And they're just spectacular things. And even stellar mass black holes can have these accretion disks. So of course, all the energy is kind of on a lower energy scale.
But it's still there.
But you can still have these things. And so they're putting out lots of X-rays and things like that we can detect. So they are very exciting things. Now I'm going to disappoint you here because I couldn't really figure out how to calculate.
If your black hole accretion disk was the size of a dinner plate, ... that's not a calculation that's easy to look up
no,
and do.
And actually I thought kind of my whole analogy here of pancakes starts to break down.
Just like everything else around black holes, even pancake theory breaks down.
Yeah.
Quantum physics breaks down, general relativity breaks down, and pancake theory breaks down.
Because I haven't come across a dinner plate with a giant hole in the middle. And I certainly haven't come across a pancake that's kind of shooting a jet perpendicular up into the air.
Yeah. Okay. So were you able to make even a best guess?
No,
Okay.
Not really at all. I mean, and again, I do apologise if your research is into the thickness of accretion disks around black holes.
You happen to be out there listening to this. I mean, listen.
Tell me.
That'd be a problem we'd love to have. We'd love to hear from you. If you write and say, well, actually, it's really easy to do, and it turns out it's about 14 centimetres. Okay, fine, good, great. But in the meantime, Emily, you're throwing your hands up in the air and just saying, no.
Yeah, sorry if I haven't come across your research paper just yet. But
if you've got a black hole on your dinner plate, you've got bigger problems.
Yeah.
Well, that brings us to the end of this pancake-tastic episode of... I don't know about you, I'm hungry.
Yes.
I'm hungry, Emily.
Yep. It's time to go flip a few.
Yeah, I think it might be. Listen, there's a couple of things that we should probably mention as we find our way out of this episode. First of all, I mean, it's still a little bit of a way off, depending on when you're listening to this. But, we're recording this in February. Coming up in May, we have a very special event. We're going to be heading down to the city of Hull, not very far away from us here in York. And they are having the very first Northern Podcast Festival. So if you go and Google Northern Podcast Festival, you will find us there on the bill. And we're going to be playing a live show, one of our great Syzygy Spaces Off, one of our live shows down at the Northern Podcast Festival, which is going to be on
16th of May.
Yes, quickly Googles it. On the 16th of May in the afternoon, about 2 p.m.
So it's a nice Saturday afternoon. It's going to be a family-friendly show.
Yeah, it's going to be a lot of fun. So if you're in the area, or even if you're not, and you feel like travelling up to the great city of Hull, then come and see us at the Northern Podcast Festival. The tickets are online now. You can go and get them for the cheap price. And I think this is fabulous. £2.67. That's just so random.
Please bring exact change to the door. No.
Yes, please. Yes, please. No change will be given. So that's that. Otherwise, if you want to get in touch with us, the usual ways are possible. Emily, how do people talk to us?
On the Twitterverse.
Yes.
So we are at Syzygy Pod, SYZYGY Pod. Mm-hmm. You can also find us on Instagram. I like to put nice pictures up there from time to time. And we are also on Facebook.
We are. The most of the social medias. We're not on TikTok yet.
What even is that?
I have no idea. It's just something that the kids do.
Oh. well.
I haven't got the
I think we're
focus.
too old, Chris.
We listen, out of the two of us, you're the one who is a bit closer. I'll leave you to work out the TikTok, okay?
I'm still battling Instagram, to be honest.
Okay, maybe not TikTok, but the others. And of course, we have a website, syzygy.fm, where you can find all the past episodes and all of that sort of thing. If you want to help us out, tell your friends, tell your family, leave us a review on your podcast client of choice, or go to patreon.com/syzygypod and become a patron of the show. Sling a few pounds our way, and it helps to keep the lights on, quite literally, because just this week we are renewing our syzygy.fm domain name and keeping our website alive. And that is thanks to all of the patrons who have pledged money over the last 18 months that we've been doing this show. So thank you to everyone for quite literally keeping the electrons pumping through our website.
You are all stars.
You are all stars, galaxies, meteors, you name it. Your universal stuff, and we thank all of you. That'll probably do it for today, so we'll catch you for something else cosmic and universal in give or take a week's time. See you, everybody.
See you later.
Bye.
So is TikTok the one with the ghost on the yellow background?
No, that's Snapchat. Come on. I literally have no idea what the icon, what the image for TikTok is. It was a dancing thing, and now it's become like you would dance and lip sync or something to music, but now it's just become another social media video.
Right.
I literally don't know.
Yeah.
And I have teenage children, like I should know, but I no.
You just go to websites these days, and there's just like this icon board at the bottom, and I'm like, I think I recognize 3 of them.
Yes. Whatever happened to the social media we had before the war? Eh? I don't know. Kids today.
It's back to carrier pigeons.